Great, thank you very much. So thank you very much to all of you for listening. This is a general session about time in physics, and there is a number of problems of time in physics which are super interesting and related to one another. But I find that very often a lot of confusion comes from mixing these problems, which are distinct from one another. I'm going to focus here on specifically time in quantum gravity, what quantum gravity is telling us about time. Being well aware that this is not the only problem, of course, and that there are questions that can be asked disregarding quantum gravity entirely, questions which are independent from quantum gravity, but also questions that, general foundational questions that might have an answer obtained disregarding quantum gravity, which might not be coherent with nature because of quantum gravity. I have written a book on time issues in general, which is the order of time, the one on the left, in which I try to disentangle and argue that when we say time, we mean very different things at different levels, and we get clarity by separating the levels and not by mixing them. But exactly in that spirit, I'm not talking about other issues, I'll just mention a few. I'll just focus on quantum gravity, and the book in which I've talked about quantum gravity is a technical book, 2004. It's Quantum Gravity, and it's all the initial chapters are devoted to somehow how to deal with temporality in quantum gravity, which was what I'm gonna cover here. I'm not really presenting very original ideas because this is basically the result of a decade or two of discussions on how to deal with time in quantum gravity, which in my opinion is a discussion closed, clarified. There are some technical aspects perhaps open or how concretely to do some calculations, but I think that I see a lot of literature coming out and reposing old problems, which in my opinions are solved. So the big discussion about time in quantum gravity came in the 60s and exploded because Bryce DeWitt and John Wheeler wrote the Wheeler-DeWitt equation, which has the form of this right equation here, an operator on the wave function, the quantum wave function equal to 0, instead of the Schrödinger equation. And so this sparked an immense debate. I mean, there's no evolution, there's no T, this is a frozen time and all that, which I think it's a confusion which has been dispelled, and we shouldn't fall back into that old confusion. So let me try to see where I think clarity here. And let me just shut down this noisy air conditioning here. So the point is that we are doing general relativity. So we are not in the approximation of Newtonian or special relativistic physics. And in general relativity, we deal with time in a slightly different way than in non-relativistic physics, which can be captured by a single experiment or a single situation, which is actually an experiment which was an ideal experiment until recently ago, but now can be done in the laboratory, which is very simple. I mean, take two clocks, here they are, this lady has two clocks, throw one upward and catch it back. And if the two clocks were indicated the same time to start with, they don't indicate the same time where they come back. This is a fact. It's a true fact of nature. It's nothing to do with Einstein, with theories, with conceptual, whatever you want. It's just a fact of nature. We understand it very well. We can do the calculation. Remarkably, for those of you who like that, the prediction, the special relativistic prediction is the opposite of the general relativistic predictions, right? The special relativity says that the left clock indicates more time, but in reality, the right clock indicates more time. Of course, the second one is the right one. In other words, there is an initial event when they are before the launch, where the two clocks are together, and a final event. And the two clocks, between these two, the time lapsed according to the clocks. If we call time what is measured by the clock is different. Good. So question, which of the two is the true time? Answer, neither. I mean, it's a fact that this is the way nature works. There isn't a true time here. And that's the situation of general relativity. In the pre-relativistic physics, we have a time coordinate which indicates what all clock measure between two events. In relativistic physics, the coordinates don't mean that. And that, Einstein said the difficulty for him to develop general relativity was to struggle the meaning of the coordinates. This was early 100 years ago. Now these things are clear. So the coordinates don't mean anything. There is nothing physical attached to them. And what we call time in all possible versions of time, perhaps except one, I'll come back to that, is a quantity which is local, dependent on the gravitational field, okay, and is different for the two clocks. This means that the entire formulation of dynamics as evolution in time doesn't fit with GR. It's a fact, and therefore doesn't fit with nature. So before GR, we love to conceptualize evolution as physical variable evolving with respect to a preferred time variable, which is t. After GR, we have many times, and so we are forced to conceptualize nature as the evolution of the variable with respect to one time or the other time, and the evolution of time with respect to one another, namely physical evolution of variables with respect to one another. And this can be done formally, easily, by slightly extending the way we conceptualize, we describe time in mechanics. Namely, instead of variables Qn evolving in time and evolution given as a function of t, and so I can graph the evolution by seeing how in t evolves the configuration variables. If this is in a phase space, I can have Hamilton equation, for instance, or any other version of mechanics that you want. You can slightly extend this formalism with a formalism which includes that. So it's not different. It includes that, but it's slightly larger by extending the configuration space, by including the time or the times, if you have many that you have. So you have variables Qi, which are the old variable plus all the possibly independent time variables, maybe more than one, I don't get into that. And then giving the graph of the same function by giving a certain number of quantity equal to 0 here, so the constant along these lines, if you want. And these, if you insert this in a phase space, can all be characterized by a single quantity having, if you want, Poisson bracket 0 with them. If you choose, okay, how do you go back? If you choose C, if you have only one time t, and it's a conjugate momentum you call pt, and if you choose c to be pt plus the Hamiltonian, you get exactly the previous case. So this is an extension. It includes the previous one, which is an extension in two senses. First of all, you can have as many times as you want, but more importantly, you don't have to specify which one is your time variable. You give exactly the same information without saying which one is time variable. So this is the sense in which the C constraint, the C quantity, contains the dynamics. There's nothing frozen. It's just a different way of describing evolution. Okay, there's nothing frozen in general relativity. It describes evolution, and that's why it's wrong to try to interpret evolution in quantum gravity in quantum terms. It's a completely classical thing. I'll come back to that in a moment. So let's go to quantum mechanics. So it's the same story. We have to go from evolution with respect to time variable to relative evolution of variables, one with the other. And this can be done by generalizing the standard quantum formulas. You choose the one you prefer. For instance, you can have this drag, you can have observables as an algebra operator, which you might or might not want to represent as operator in Hilbert space, evolving in T, that's evolution in T, according to the Heisenberg equation, the Heisenberg picture. If you represent the operator in Hilbert space, you can flip the evolution into the state, and then you have the Schrödinger picture. Now, you can extend that by going to partial observables, namely the extended configuration space. Again, you can represent, you have an algebra of observables, you can represent it in Hilbert space K, which is a different interpretation of the previous Hilbert space, because it includes independent variables, right? Include the time. evolution is given as before, and the equation is given by the commutator of C with these quantities equals 0, which again, if you flip on K, just picks up some states on K. I'll see in a moment how do you use that. I'll skip that because the time is very little here. I'm trying to go fast. So how do you use that? These partial observables, remember, time is among them, are operator on this expanded Hilbert space. The constraints define a subspace, a proper or improper subspace, sometimes it's called, and this automatically defines a map from K to H, a projector if it is a proper subspace, an extended generalized projector, Bayer calls it an extractor, which can be written explicitly as a map from K to H, and this has matrix elements. And if you look at this matrix element of this projector here, between sandwiching the operator between eigenstates of the partial observables, you get the transition amplitudes, and that's give the evolution quantities in quantum gravity. If you are in the special case in which C has this form here, so you are in the usual case of evolution, it can be shown that these transition amplitudes are precisely the standard transition amplitudes from a configuration space to another configuration space evolved in time. But this is much more general. You go from one configuration space time to another configuration space time. And of course, you can do that with a path integral if you want by the standard way in which you translate algebraic or operator calculation in path integrals. This can be done in general relativity, and it is done in general relativity, and the cleanest way is to consider transition from a state on a space-like surface to another space-like surface. So again, it's evolution. Formally, you're integrating all everything in between, where those states here are in the extended configuration space. And this is not abstract because I may just flash a slice about loop quantum gravity, where this is done explicitly. There is a construction of the extended configuration space, the operator, and a specific definition of the transition amplitude. From that, you extract probabilities. I'll just skip this unless you have questions about probabilities, because time runs very fast. So, what is quantum time? What is time in quantum gravity? A key point is that in general relativity, there are many time variables. They are measurable. They're not predictable, exactly like time in Newtonian mechanics. You can measure what time is it, but you cannot predict what time is it. You can predict something, what happens at a given time. And the same is true in quantum gravity. You have independent variables. You have a number of variables. And what you can predict is relation between these, given something that you know about these variables. So there is no mystery about emergence of time in quantum gravity. And in particular, it's not that quantum gravity time is frozen, because you can take standard evolving Newtonian physics and express this in language. So this is not a language about frozen time, it's a language about evolution as change, transition amplitudes between observable quantities, some of which are not predictable because are the one with respect to which you see the evolution of the others. But the key point is that you don't need to specify them. This has strong consequences because these times that are measured by clock are quantum variables, so they can be superposition, they can be discrete. And let me just take 2 slides for commenting two cases which are extremely interesting because there are 2 experiments recently proposed, and the first one seems to be doable. It's to measure a non-relativistic quantum gravity effect in the laboratory, and the idea is to take two nanoparticles, quantum split both of them, so you have 4 branches, sort of left, 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 right, right, left, and right, right. And in one of these, there's the right, left, you keep the 2 particles a short distance from one another for a certain amount of time. And then what happens is that you have 4 branches, and in this branch here, look, this this particle here stays at the same position for a certain amount of time, but the metric, it's a superposition of the metric generated by this particle here and the metric generated by the particle here. So for this particle here, the time from this point to this point is not fixed. It's a superposition of two times. And if you compute the difference between the two, you have a delta S, a difference in proper time along this line, which is very small, but it's measurable, and which gives a difference in the phase of the evolution of this branch with respect to the other one, which, according to the experimentalists, can be measured. It's given by this quantity here: Newton constant, Planck constant, the mass of the particle, the distance, and the time in which during which they stay together. This is a small t. Even more interesting, but this is more far away for the possibility of measuring it, is the fact that if you actually put numbers, how small is the difference of proper time? So the same particles that stays there has the superposition of two different proper times. It can be expressed by this formula here. So m is the mass of the particle. If this not too far from the Planck mass, which I remember is a microgram or a fraction of a microgram, so this is doable. The difference in time is order of the Planck time, right? Which means that this might give us an access to Planck time through interferometry, which is notoriously extraordinarily sensitive. So the entanglement between the two particles, which is how you measure the effect, could be sensible to the discreteness of Planck time, and we could measure the discreteness of time. So time is a lot of things, but if we separate them clearly, I think we don't get confused. And let me just go through a list of different notions, different meanings that we attribute to the fact that there is time in nature. The largest is that it's, say, the opposite of something is frozen, something is static. So things happen, right? And this is true in physics. All physics, special relativity, general relativity, classical, quantum gravity. This is about happenings, about change, about evolution. There is nothing static in the block universe. There's nothing static in the solution of the Einstein equation. The solution of the Einstein equation is this mathematical description of a set of events. So in that sense, change is in quantum gravity, okay? A more specific definition of what we mean by time is a counting of a sequence of events, right? Like in Aristotle. And that's existing in quantum gravity, like in general relativity. I mean, in general relativity, I have a clock and I can count the ticks of the clock, and that's a counting of events in the sense of Aristotle. It has nothing to do with Newton, has nothing to do with geometry of Euclid or anything like that. It's time in the sense of counting event, right? This is not put in any question by modern physics. More specifically, we can say that time is the reading of a clock. And in general relativity, there isn't a single time, then there are many times, because as we have seen, different clocks measure different times along different paths. So then we don't have any time anymore. As soon as we define time in this way, or if you want to say which one is the variable describing time, we're lost in GR, because that's nature. There isn't a variables. The idea of continuous time, which should take us fundamentally, if you start from exponential time, and I think you make a mistake because experience is notoriously wrong, it's an approximation if what seems to indicate current quantum gravity theories, time is discrete. And the idea that there might be a complete orderings of events as opposite to partial ordering, it's just ruled out by special relativity. There's no complete ordering of event in nature, that to which we have access to. Maybe there is the mind of God, but doesn't concerns us. Minkowski space-time approximation, Newtonian space-time approximation, and even more, and since other people will talk about that, I'm getting close to the end of what I'm saying. I think that the time of our experience depend, of course, by the fact that we are in a certain approximation, in a certain regime, classical, we can disregard quantum effect, we can disregard all sort of thing. And we are in a contingent situation in which the past is very different from the future, and we have a brain that works in a certain way because of that and related to that. So there are issues about time which has to do with the orientation of time, the difference between past and future, and causation, which is strictly related. I think that causation follows the physical orientation of time and not the other way around. But these are high order notions. These are not notions that should concern a quantum physicist that work about what do we know about the relations between the events, how they happen at the level of at the most general level that we have tentatively to describe the world so far, which is quantum gravity, because these require a macroscopic thermodynamically requiring some way or the other to distinguish degrees of freedom that we control, degrees of freedom that we don't control. So they are not about fundamental physics. So I close. I'm using 20 minutes. I want to give time for discussion because I think the interest of this meeting is only because we can ask questions to one another and object to one another. Is there evolution, change in quantum gravity? Yes, of course. And you don't need Page-Wooter, you don't need quantum mechanics, you don't need, of course, there's nothing frozen in general relativity nor in quantum gravity. This is about how things change. Is there a time variable? No, there is no time variable because there's many time variables. There's anything we can use for counting change is a time variable. Change is local, it's not global, and so on and so forth. How do we actually compute how things evolve? With just the transition amplitudes, which were defined in with respect to a preferred time variable in non-relativistic quantum mechanics and classical mechanics, just with variable one with respect to the other one in sort of generalized classical mechanics and generalized quantum mechanics, including quantum gravity.
So the galaxies have one distance, right? If there's a difference, it's a systematic. It's not, it might be astrophysics, but it's not early universe physics. So yes, we need to straighten that out before we can put this problem to rest.
So I would like to just mention something which was sort of relatively new to me, but again, I may not be at the latest update on this.
Is that was an interference?
I don't know. I guess.
Yes, it was from another session. I recognize the voices of people.
Okay, so I'm stopped. I've only taken 20 minutes because I wanted some time for discussion. Thank you.
Thank you very much. It was a really great talk. And yes, exactly. We have 2 minutes. Question, please. Is there any questions, discussion?
Yeah, may I ask a question, Carlo? It was very interesting, and it's a completely different world that you live in compared to my world. Is your time evolution deterministic? When you just look at the Wheeler-DeWitt equation, it's a deterministic equation. So do you reconcile the passage of time with a deterministic view of physics?
No, I think, and this has nothing to do with the Wheeler-DeWitt equation. I think quantum mechanics is not deterministic. The Schrödinger evolution is deterministic, but the Schrödinger evolution gives probabilities to us. So the lack of determinism is already non-relativistic quantum mechanics, even more so in quantum gravity. Of course, this does not prevent you. I mean, any non-deterministic theory, you can rewrite this as a deterministic theory by adding to the present hidden information about the future, right?
Yes. Mm-hmm.
And that's what happened in hidden variable theories or in many worlds interpretation. You add ontology saying, well, the present is not what is accessible to us, but is much more vast and include information about the future. So it's meaningless to say that the theory is deterministic or non-deterministic in that sense, because you can always translate one into the other. But in the strict sense, I mean, given all what is accessible to one observer in whatever sense you mean, can the future be predicted? In fact, even the past be predicted, postdicted? The answer is no, as far as we know, at best from physics.
Thank you.
All right, very good. You're seeing my screen, yes? Good.
Yes, very well. Thank you.
Okay, so yeah, so thank you everyone for coming, and thank you, Shikufe, for inviting me. I am a philosopher. I'm not a physicist. I hope what I have to say is going to be some interest to physicists. And I'm not going to be talking about quantum gravity because I don't know much about quantum gravity, but the talk is going to be about something that Carlo touched on about something that one would not expect to get out of fundamental physics. And when I first, when Shikufe first invited me to this session, my first thought was, well, I don't know if I'm going to have anything to say. And then as I started to sit down and actually think about it, of course, the worry is whether I have, I'm going to be able to fit what I have to say into 20 minutes. Okay, so what the talk is about not fundamental physics, but the familiar temporal asymmetries of the macroscopic world that are ubiquitous parts of our experience, how we explain them, and what we should and should not expect to get from fundamental physics if we ever have a fundamental physics theory that's comprehensive and complete. And there's a sense in which I'm going to be elaborating on a remark that Carlo made and passed over fairly quickly. On one of his later slides, he had these things about time, and oriented time, he said, is a macroscopic statistical phenomenon, and he doesn't expect quantum gravity to change that, and causation is a higher order notion, not a fundamental one. And the two things, I think, go together. And I want to talk about how they go together. So I'm not sure whether Carlo and I agree on everything I'm about to say or not, and we can find out during the discussion. Okay, so one of the things I've been thinking about lately is foundations of statistical mechanics and how it is that one actually gets from statistical mechanical background with microphysics that is symmetric under time reversal, equations like the Boltzmann equation or like the Langevin equation that are first order in time and are not time reversal invariant. And one thing that I find striking about, studies of the process of relaxation to equilibrium. And one thing that I find striking about this process of equilibration is that what you get on the macroscopic scale is a merging of pathways, a sort of erasing of the past. So take an example of free expansion of a gas. So a gas is initially confined by a partition to one side or another of a container. You pull the partition out, wait, you don't have to wait very long, you know what happens. It fills up the thing, right? And it does that whatever side the gas is on in the first place. And if I gave you a box of gas and I told you that it was either to the left or the right of the partition an hour ago and said, okay, find out which one, I think the correct answer to that is no, can't do it. Even though, if you take the microphysics seriously, if you think that it's going to be some kind of quantum unitary evolution, the initial states are orthogonal to each other. And so the state after this process of everything, the box and everything that it might have affected, they're actually orthogonal to each other. But the details are, buried very deeply in inaccessible details of the microphysics, and there's just no way we're going to be able to distinguish those two orthogonal states. So at the this phenomenon is utterly routine, ubiquitous at the macro level. At the micro level, whether it's classical or quantum physics, distinguishability of states is conserved. So classically, if you've got two sets of states that either do or don't overlap and evolve them, then the measure of their overlap is conserved. And if that measure is 0 at the beginning, it's 0 at the end. In quantum evolution, as long as it's unitary evolution, it preserves an inner product. So if those states are orthogonal at the beginning, then they're orthogonal at the end. And this is true whether or not the dynamics is invariant under time reversal. There's been a lot of discussion about how, in the philosophical literature, about how to, what is the time reversal operator, how to represent it. None of that is at all relevant to the issue here, because as long as you've got Hamiltonian or unitary evolution, it doesn't matter whether it's, you're going to have this phenomenon, and you're going to have a tension between merging of pathways at the macro level and the conservation of distinguishability at the micro level. Okay. So there's a common way to think about this in the literature on foundations of statistical mechanics that over the years I've been becoming more and more discontent with. And what I want to do is very briefly explain my reasons for discontent with this, and gesture towards an alternative way of thinking about it, something that has been raised by other people in the literature on foundations, but I think has been unjustly neglected. So a common response is that, okay, temporal asymmetry is not going to be found in the fundamental dynamical laws. What else? Where else could it be? It's, when you're making a prediction, you've got dynamical laws and initial conditions, so we're going to find it in initial conditions. What else could it be? Okay. And one approach is to say, let's put all of that into a one-time posit. So, cosmology seems to be telling us is that the early universe started out in a far from equilibrium state, and things have been evolving ever since. In the philosophical literature, this has come to be known as the past hypothesis. I think it was David Albert who coined that term. And you can make one or two attitudes towards this posit about the past. It can either be, okay, we don't explain initial conditions. This is just a contingent, unexplained facts. It's the laws that explain. Or you could say, well, no, that's just too big of a coincidence to be unexplained. It's a consequence of some law constraining the early state of the universe. So in that vein, we have Roger Penrose's Weyl curvature hypothesis. And I think that if you stop and think about how we actually explain things, those aren't the only options. So, and I don't think that this way of talking about things really gets to the heart of the matter. So let's think about what people do. Like people who are actually working on non-equilibrium statistical mechanics, trying to explain equilibration, right? Starting from the microphysics plus certain kinds of assumptions to get temporally asymmetric equations. What do you actually do? And so, I mentioned the Langevin equation before. I think that's a good thing to think about. Think of some object that's moving in a resisting medium, right? So, I like to imagine a spherical mass on a spring oscillating in a resistant medium. And we know what it's going to do. If it's oscillating, it's going to slow down and eventually come to, well, not exactly a rest, because if the thing's small enough, it's going to come down to a state where it's sort of jiggling around with Brownian motion. So it's going to settle down not to a stable state necessarily, but to a stable pattern of fluctuations in position and velocity. And to make things simpler, imagine that it's, a rarefied gas. So these little blue arrows are supposed to be molecules that are bouncing off things. And imagine for the moment that we can treat this sort of thing classically. course, the word world is not classical, but my claim is that you're going to say very similar things in a quantum context. Okay, so what do we do? Okay, well, if you're going to get an equation, you know, that gives you the velocity, you know, probability distribution of velocity as a function of time, or, you know, how it decays. You know, in a case like this, a simple assumption would be that, okay, the average kinetic energy of the gas molecules hitting the sphere is isotropic. You know, it doesn't matter where the sphere is or how fast it's going. The state of the medium is pretty much the same. And this is why I'm restricting the case to a rarefied gas for the moment, because if you're a hydrodynamic regime, then that's not going to be true. But I claim that similar considerations are going to apply there. Right, and so if it's heading in a certain direction, then the things that are going to be hitting it from the front are going to, on average, have a greater relative velocity, and on average be imparting more of their kinetic energy to, exchanging more kinetic energy with the thing. And so there's going to be a net tendency to slow the thing down. And you can write down equations and get a Langevin-like equation from this. Okay, so that's the sort of assumption that is typically made in these studies of equilibration. It's, of course, goes back to the sorts of assumptions that Boltzmann was making when he was doing his study of gases relaxing to the Maxwell-Boltzmann distribution of velocities. This assumption that Boltzmann called the hypothesis of molecular chaos. It's come to be known as the Stoffzahl-Ansatz in some of the foundational literature. Okay, so let's take for the moment that that's the right assumption to make. Yeah, it's not. Why? Why should we assume that? Well, there's a popular answer that I think is not on the right track. And that answer has to do, actually, let me just, sorry, I'm getting ahead of myself. So why do we assume this? And, you know, we wouldn't assume that the situation, you know, we would tend not to assume that the situation is such that the medium is speeding up the thing and increasing the amplitude. Right? Well, suppose I told you that actually, no, I do think that the state of the medium is like that. Suppose I told you that on average, the kinetic energy of the molecule is hitting the sphere behind the greater, resulting in an accelerated force, and so the thing is speeding up and increasing its amplitude. You would say, Wayne, I don't believe you. I think that's what you would say. I don't believe the state of that. You know, I think you would correctly regard this as unlikely and unlikely to persist, even if it were true momentarily. Okay, now the question I want to ask is why? Why would we regard that as unlikely? Oh. Okay. There's a tempting answer, and I think it's connected to a temptation that goes back through the history of discussions of probability theory, which is a temptation to think that probability is just a matter of counting numbers of states. So the tempting answer would be, okay, yep, the set of states that satisfy at least approximately that isotropy assumption is just a lot larger than the set of states having an accelerative effect. We regard, you know, the accelerative states as unlikely just because it's such a small set of states. Here's why I'm not happy. So that's what a lot of people would say. Here's why I'm not happy about this. Right. Suppose I tell you that the distribution of energies of molecules that are near the sphere and moving away from it is not isotropic. In average, the ones in front of the spheres have more kinetic energy behind it. Would you have the same response? Would you say, Wayne, I don't believe you. That's just too small a set of states. No, of course, you wouldn't. That's what you actually do expect for something that's in the process of equilibrating. So my claim is that when we're making these judgments of things that are likely and unlikely, we are not, in fact, making them on the basis of size of sets of states alone. There are other considerations that are coming into play. Now, some people, and by the way, I think that that's the right answer. And some people who are very much wedded to this idea that we should regard things as likely or unlikely in terms of size of sets of states would say, okay, I wouldn't regard that unlikely, but that's just because I'm prejudiced. What I really should regard that as unlikely. In fact, I should regard everything I've ever seen as unlikely and everything that anyone has ever seen as unlikely. I think that's incorrect. And I don't think you should try to get yourself into a state of mind where you regard everything that anyone has ever seen as unlikely. Okay. All right, so if I did tell you that on average, things moving away from the sphere have more kinetic energy than ones behind it, and you said, okay, I believe that, then I ask, well, how do we explain that? I think the answer is simple. It's because they recently collide with the sphere and exchange energy with it. Here's what I want to claim. That is a full answer. You can put a period on it. That is an answer, an explanation. Now, the accelerative state is just the same as the state you do think is happening, the retarding state, with all the velocities reversed. So if someone thought that the state of the medium was in an accelerative state and was speeding up the mass, could we give the same explanation just by reversing all the velocities? Right. So suppose I told you the distributions of molecules are near the sphere and moving towards it is not isotropic, and on average the ones behind the spheres have more kinetic energy than the ones in front of it. That is, suppose I told you it was an accelerated state. Could I just give the same explanation with the velocities reversed? Say this is true because those molecules are about to collide with the sphere and exchange changes with it. No, you wouldn't take that as an explanation. Routinely, we explain, states of things in terms of interactions they've recently had with other things, and not in terms of interactions that they're about to have. And of course, that notion of explanation is very much tied up with the notion of causality. So, I think that that's actually the right way to think about this. We should expect for the incoming molecules something like isotropy on the basis of an assumption that has the flavor of a causality assumption. It's an assumption that we can make about the states of things at all times. It's not an assumption about initial conditions way back in the early universe. So, so that was brief. This is work in progress. I'm going to, at some point, write a paper about this. Here are the things that I expect to be able to conclude with more detail. So when we're asked, how do we explain temporally asymmetric phenomena, like the tendency of things to equilibrate, like a ball on a spring slowing down and coming to, almost rest? The explanation is not to be found in either in the fundamental dynamical laws or in some kind of one-time assumption of the early universe. It's founded on conditions that we can apply at any time, which are closely allied to our ideas of causality. We get temporally asymmetric explanations, ones that don't work if we just change the reversive velocities of everything. because I claim the very notion of what it means to explain something is temporally asymmetric. Our notions of what it means to explain something are tied up with our notions of causality and are which is tied up to the idea of temporal asymmetry. Carlo said something that he thought that the notion of causation and the notion of the temporal asymmetry are closely connected, and I think that's right. I think that I wouldn't say that one is more fundamental than another. I think they're basically two sides of the same coin. And it doesn't need to be the case that either of those things happen. If the universe were in a state of thermal equilibrium, there wouldn't be any preferred temporal direction of processes, and I claim there also would not be cause-effect relations in a world like that. Okay, now, if I accept all this, I want to be clear. There are certain things that have not addressed. You might ask, well, okay, in order for any of these things to be happening, we have to be in a state of far from equilibrium, and that's yes. Why? Okay, well, has to do with how the universe started out. It could have started out in the state of thermal equilibrium. I don't know enough about the physics of the early universe to know whether it's surprising or not that the universe started out in a state far from thermal equilibrium. Deep, important question. Yes. So that's been 20 minutes, and leave time for discussions.
What I would like to do is really talking about this issue of time in fundamental physics. And I'm going to give a very broad kind of overview, which just because of we don't have enough the time to discuss everything in detail. And also, however, I'm going to focus on issues which were raised on quantization of time at the Perimeter Institute, particularly by junior researchers in the chat box and the discussion sessions and so on. So some of the things may be well known to the expert. Okay, so let me just begin with a quick summary of a very, very long history. The quick summary is really starting from this notions of space and time have evolved very much. And already we can start with Aristotle, a long time ago. And in Aristotle's model, I mean, in all these models, my assumption is that the notion of an event is an a priori notion, and that I'm looking at the space-time from the modern perspective of differential geometry and putting the events in the perspective of differential geometry. Then the events actually form a four-dimensional manifold. And in Einstein's model of space and time, here is a four-dimensional manifold. Absolute notions. The notion of time is absolute, notion of space is absolute, which means that, in fact, that this space-time manifold is actually nicely foliated, by very preferred spatial section. But there's also a rest frame, which is really absolute, which means that if you give me a particular point up here in space, I know what I mean by the same point at a different time up here. In Newton's case, the point is that the rest frames are no longer absolute. We still have absolute time, absolute space, and that we got the time intervals are absolute here. But the space intervals are not absolute because they're observer dependent. If in fact Newtonian physics, which is moving straight like that, then in fact this point will be regarded the same as this spatial point. But if I have an observer moving like that, then this point will be regarded as this spatial point. So therefore, the spatial distances between points are really frame dependent, and that is a Galilean invariance that we know. Finally, I just wanted to also note one thing, which sort of perhaps if there's time we'll come back to, that Newton's absolute time, which is what really started the whole thing with Principia. I think that it really is not physically satisfactory at all. And Leibniz's notion of relational time, how things evolve with respect to each other. It is relational time that Carlo also mentioned. I mean, but in more mundane term, basically is that not that there is a grandfather clock which is ticking up here, but rather questions we ask are relational questions, such as, once, if you take the Earth, moons, and a sun system, then we can ask, well, while the Earth goes around the sun once, how many times has the moon gone around the Earth? This relational notion of time is something that Leibniz actually preferred. But as it turns out, I mean, we already know that even though that is a better and clearly more physical notion of time, in fact, if I had done all the calculations with Leibniz's notion, we would not really have made such rapid progress in already just after the Principia as we were able to do, people were able to do using absolute time. So what is really conceptually correct need not be the most useful way of making progress in the small time scales. And finally, we got Einstein's time up here. And then here, the statement is that this special relativity, we got 4-dimensional manifold, the absolute structure is the light cone at each point. And we got Lorentz transformations. And the point now is that even the delta x and delta t are observer dependent. And because we got one notion of time up here, one notion of simultaneity here, and there is another notion of simultaneity here, and they're completely different from each other. Then we can go to the best model of classical model of space-time we have today, which is given by general relativity. And for simplicity, because of time up here, I'm just going to look at manifolds which have certain topology and are globally hyperbolic. So the notion of evolution is unambiguous. So in this case, the statement is that what is absolute is really the causal structure. At each point in space-time, in the tangent space, we've got a causal, we've got a null cone, and that tells us points in space-time which are causally related to the given point, time-like related, null related to this causal point, or space-like related to this causal point, to this given point up here. There is no global inertial frame. I mean, even in special relativity, we have these global inertial frames, and therefore delta x and delta t are now location dependent because the metric depends on space-time, and they're also path dependent, as in fact Carlo had explicitly had a little picture there about clocks, which showing that it is path dependent. Now, there's a huge difference in the choice of constant T surfaces. Even in Minkowski space, we had this plane, space-like planes of distance of simultaneous events, and there was only a Lorentz freedom in that, just a finite dimensional freedom in that. Whereas now we've got infinite dimensional freedom, and that is a multi-fingered nature of time. So if you give me one space-like Cauchy surface and say that this is one instant of time, the next instant of time could be this one. And then the point of the multi-directional dimensional multi-fingered nature of time means that if I move a lot perpendicular to the given surface up here, then I will move a distance which is given by n of x, and that n of x is an x-dependent thing, and that is what gives you a multi-fingered notion of time up here. So for example, so we'll come back to this, the other diagram in just a minute. So there's a notion of time evolution. So if you give me an initial slice up here, then, and if you give me the initial data, so there's a 3 metric, which I call QAB, because like configuration variable is canonical conjugate momentum, and also matter fields on this data, on this initial surface, I can evolve it and obtain them everywhere. And so we can start from sigma 1 here and obtain to sigma 2 here. Or as in this picture, I can fix my sigma 1 and sigma 2 to be here. But in going from here to here, I can go by space-like surfaces, which just march in time like that visually, or which are much more fancy, which are wiggling, but ultimately they again reach sigma 2. And if I did these two different evolutions, will I get the same answer for the initial data, for the fields on this slice, if I once I pre-specify them on this slice? That is a key question that is really raised immediately once you accept the multi-fingered nature of time. And the point in general relativity is that the answer is yes. And the answer is yes, because the Hamiltonian is in the Hamiltonian description, it's a constraint system. In other words, the Hamiltonian is given by this n of x, which actually relates these two points, or point on this surface, to what I mean by the same point on the next surface up here. That is given by this n of x times some function of the phase space variables. And the point is that this particular function of the phase space variable is actually vanishes on the physical surface. I do need a larger phase space to even talk about Hamiltonian dynamics. Obviously, if I just look at just a phase space, the constrained surface, then there will be nothing. But the point is that there's a big phase space. So here is a phase space, not space-time, gamma up here, and there is a constrained surface, gamma bar, and my points Q, P, etc. are all really lying on this constrained surface. And the dynamical orbits are also then in that constrained surface. So the consistency between here and here is guaranteed by the presence of a constraint. Now let me completely switch gears and talk about quantum mechanics. And to begin with, even non-relativistic quantum mechanics, but we can really talk about even field theory and or more general spin systems and so on, as we'll see. But to keep the discussion more quick, let me just talk about particles in one dimension for most of the time. And so now I'm switching gears. And now what is the notion of time up here? So here we got Hilbert space of states. So states are not given by P and Q, like in the phase space up here, like P, Q, and phi and pi in the phase space, but they're really given by these elements of the Hilbert space, square integral elements up here. And then on that, observables are self-adjoint operators. Particularly, I got a momentum observables up here, and I got the position operator, and they satisfy the. These are self-adjoint operators. And we also have the Schrodinger equation, which tells us the time evolution. And if I look at the definition of the momentum operator, and if I like the definition of the Hamiltonian operator coming from the Schrodinger equation, you are tempted to think that P is canonical conjugate to X. Just as this is true, H is canonical conjugate to T, except for a sign, because I got a minus sign up here. So it's tempting to write canonical commutation relations between T and H, except for the sign, which are the same as up here. Now we know, long time ago, Pauli said that this is impossible. Time is really a parameter, cannot be an observable, cannot be a self-adjoint operator if the Hamiltonian of the system is bounded below. This psi refers to the wave function of the system. This refers to the Hamiltonian of the system, momentum of the system, position of the system being a particle. So he says that is impossible, and the answer is very simple. The proof is very simple, that if in fact you got a self-adjoint operator like X, for example, if I go to the momentum representation, then if I can make a unitary operator out of it, and then it has this action. So therefore I can just shift the argument here by constant amount. So if in fact I had a time operator, I could also consider e to the I, alpha is a constant times t hat, and then I can go to the energy representation, and that will just shift the argument of the energy. Alpha is just a arbitrary number, and therefore this alpha can be anything. So I should have states with arbitrary low energy up here. That should be in the argument up here, and that is not for the Hamiltonian is bounded below. That is not possible. So therefore the idea was that X in fact is definitely an observable, and T should be a parameter up here. I think let me just change this just for a second, because I think it'll be easier for you to see if I change it. Yeah. And so we got here. And now we got, this is a question that people often ask, but I got X and P as operator, and then I got uncertainty principle, but we also have this uncertainty principle. So isn't there an operator corresponding to time? And the point is the meaning of delta X and delta T is entirely different. Delta X is really an uncertainty in this sense, in the sense of expectation values, where delta T is really a time interval. It is the amount of time that takes any given observable to change its expectation value to change by an amount delta A, which is really the dispersion in the observable given by that. And delta T, therefore, actually, in this thing, would depend on the choice of this observable, but no matter which observable you choose, you got this. Therefore, the statement is that this uncertainty principle is on entirely different footing from this. This is really fundamental. This is in some sense a heuristic one, in which delta T has a different interpretation. And then Pauli and Peter Bergman told me that Pauli used to say that, well, this is really important. There is a difference between X and T, because where is a particle is a meaningful question, but when is a particle is a meaningless question. But as we'll see, Pauli was not quite right. And the reason is that mathematically, the Pauli argument is quite correct, but it misses the main point. What we need is to extend the framework to include a clock, which time is not an observable in the system Hilbert space, but it is observable in the clock Hilbert space. The clock Hilbert space is just square integral functions of R, and R is this little t, if you like, and dt, right? This is the measure that dt I got up here. And now I got the Hilbert space of the clock, and I got a Hilbert space of system, which is the same as before. And now in the Hilbert space of clock, I do have these nice observables. T is a self-adjoint operator, P is a self-adjoint operator. And indeed, as Pauli told us, P hat, the adjoint the canonical conjugate operator, is unbounded below, given by this definition up here. But the key point is that now in this combined system, dynamics is given by constraint. And I'm a little bit using slightly imprecise notation just because of the time limitation up here. Namely, that the statement is that physical states in this combined system, which I'm calling H kinematical because the physical states are going to satisfy this particular constraint, and that is also the notation that is often used in quantum gravity literature. And the point up here is that on this system, then I can write down an operator. The Schrodinger equation that is up here can be just written as operator up here, but it operates on a clock Hilbert space. And then I got the Hamiltonian, which operates on the system Hilbert space, operating on psi, which is this up here is called a bipartite state, which roughly speaking is in fact the state in this kinematical Hilbert space. So this equal to 0 is really the constraint, and this really is just the Schrodinger equation. So the whole point is that you have to bring in the clock Hilbert space up here in addition to the system Hilbert space, time is the self-adjoint operator, but now the dynamics is given by this constraint. And this holds generally. This also is true for the relativistic fields. Now the states of the system are given by square integral functions. This really rigorously defines square integrability in infinite dimensions of the field configurations up here. And you've got a kind of a time evolution equation of the state, which is really given by very like the Schrodinger-like equation that I got. And this is all completely rigorous. I will tell you the self-adjoint operator. And the point is that in this whole discussion, the Pauli or Bergman statements really are incorrect, because neither is a where is a particle well defined, nor is a when is a particle well defined. What is well defined is really, you have to give a condition. You give me a time interval, and then I'm asking, what is the probability of finding the particle in a given space interval? If you a priori specify a time interval, within this time interval, what is the probability of finding the particle at some position X? Or conversely, if you give me a position interval, and then I can ask, is there a time in which the particle has that position? So in terms of conditional probabilities, they are brought on a similar footing. Now I talked about general relativity, and I told you that there is a multi-fingered nature of time up here very nicely. And that is all consistency is given by the fact that the dynamics is given by constraint. I told you that quantum mechanics also, we have got dynamics, which is consistently given by the constraint up here. And now the point is that we are bringing in quantum mechanics and general relativity. Now, for simplicity, I'm going to just talk about quantum cosmology, just because of there are many technical issues which are open in full quantum gravity, and here everything is under control, because the system now has finite number of degrees of freedom in quantum cosmology. So in full theory, I got the metric and the scalar field as my configuration variables up here. And now from this infinite number of configuration variables, we're just going to go to scale factor and anisotropies and looking at homogeneous cosmologies, and then the scalar field, which none of them depend on anything, they are just numbers. And therefore the solution is really given by A of t, bi of t, and phi of t. But we got the reparameterization freedom, and that is a residue of the multi-fingered nature of time. I can reparameterize this time to another t prime, which is a function of t, and that freedom is still there that we got. And the point is that we can therefore really eliminate this spurious time, for example, by not talking about A of t, bi of t, or phi of t, but looking at relational or conditional evolution, namely, when the value of the scalar field is so and so, what is the value of the scale factor? The value of the scalar field is so and so, what is the value of the anisotropy. And then phi is therefore a relational or internal time. And now we can again build a kinematical Hilbert space, which is really now, however, of all these variables of A, phi, B, and phi up here. And this is really the Hilbert space of the matter and the geometry. Idea here is that we should think of this phi as clock, and this is the system, if you like. And then the constraint from the general relativity that we have got, classical constraint, just becomes the so-called Wheeler-DeWitt equation as a wave function up here. There's no time here. This is a constraint equation, but because if I take this phi, implicitly I assume that this phi is a massless scalar field, then the statement is that we get a nice Schrodinger type equation up here, which governs the evolution. And the conditional probability is well defined. Given a value of phi naught, the relational time variable, what is the expectation value of the anisotropy of the curvature? And these questions have been answered. The questions about whether there is a bounce is a physically meaningful question, and we have answered those things using very different frameworks, including the path integral framework that Carlo was alluding to, but also other generalized quantum mechanical frameworks. So let me summarize. I have provided a global perspective on the evolution of our understanding of the issue of time. I obviously had to gloss over many subtleties and important technical points, but the focus was on a conceptual thread. The notion of time evolved really dramatically, starting from Aristotle to Newton to Einstein's special relativity to Einstein's general relativity. But these evolutions are conceptual. But the important thing is that each time a revolution took place, there are no new observable windows opened up continually. For example, in particle physics and GPS systems, we use really in particle physics, it's because time intervals are dependent on the frame, reference frame. It's very, very important when we talk about what the lifetime of particles are. There's a lab frame and the particles rest frame, and the two are very different. The GPS system, there is a computation between special relativity and general relativity, and they go in the opposite directions. But finally, the general relativity effect is what is really turns out to be more important. And then the quantum information, now people are using various beautiful experiments to really bring all these things together. A pleasing feature is really coming together of physical and operational ideas and fundamental concept from general relativity, the multifingered nature of time and the associated Hamiltonian constraint, and a post-Pauli understanding of how time should really be thought of in quantum mechanics and quantum physics. And the difference is that in quantum physics, what we had to do, quantum mechanics, what we had to do was we've always focused on a system because we thought time was an external thing, and we had to bring it in and extend the system by considering H clock and H Hilbert space. Whereas in quantum mechanics, in general relativity, as we know that there is no such thing as time. So there is nothing specially, it's a special variable time sitting there. And therefore our H kinematical was really already contained in the dynamical variables of general relativity, or in full general relativity, it will be these variables up here. And the statement is that here we are given with, if you like, H kinematic, the full Hilbert space, and then the constraint is imposed on that. And we can interpret the constraint as really for a given time. So there's no canonical notion of time, but you can choose a particular dynamical variable as a clock and see how other things evolve with respect to that. Now, it doesn't at all mean that everything is understood and well controlled. I want to emphasize this. There are many refinements and extensions, and many technical issues are really open. There are several things like that. But I think that there is no conceptual roadblock to this understanding. So I think I've gone 1 minute over, so I'll stop. I got 21 minutes right now. If there are any questions, I'll take them.
Thank you very much for the great talk. Thank you. Is there any quick questions? Because we have less than 2 minutes for the next speaker.
If there's no question, I just want to make one comment about what Carlo said. I mean, Carlo and I, we think very analogously, very parallelly. I mean, Carlos said that fundamentally, however, there are also some differences. And one difference, I mean, it's not a huge difference, but there's still a difference. It is really that Carlos felt that meant that the time is really discrete in quantum mechanics, in quantum gravity. And my view is that we don't know that. I mean, there are specific proposals like spin-form models in which events occur and you can do counting and talk about discreteness, but that really presupposes what the histories are on over which we are going to sum over. The spin-form framework gives us a particular history and a particular class of histories, there are quantum geometries, and in that, indeed, the events happen discretely and therefore time is discrete there. However, I mean, there may be other consistent quantum gravity frameworks in which the quantum geometries are chosen differently and we may have different answers. So this is just a minor clarification from my perspective that I wanted to make.
I just make a small comment, just one line.
Please.
I agree. I agree. I mean, I didn't mean to say that we know that time is discrete. I mean to say that there are some indications that it might be discrete and very interesting. There could be some in the future, not now. Some experience right. That's not totally outside the possibility of measuring. I'm just saying it might be discrete without being into contradiction with the fact that we use a continuous time in our common approximations.
Thank you very much for organizing this interesting session. So I will share my screen. Here it is. So my contribution to this session is from the point of view of the statistical physicist and the I meant one transparency too far here. From the point of view of the statistical physicist and the condensed matter physicist. So the question that I'm starting with is one that some of the other talks also starting with. So on the one hand, we have these supposedly fundamental laws of physics that are deterministic and time symmetric. On the other hand, we experience reality as indeterministic and irreversible. And we usually think that those two features are related to the passage of time. And there are different ways of dealing with this contrast. One is to try to derive this indeterministic, irreversible nature starting from up here. This is not the way I want to take for reasons that I will explain somewhat later. I want to go in another direction, namely a bit like Wayne, first questioning our concept that all the fundamental laws are deterministic and time symmetric. There are other laws that aren't deterministic and time symmetric that might be as fundamental. And I also want to question that the deterministic and time symmetric laws are always applied in a deterministic and time symmetric way. So there is indeterminism poured into these laws. And that's what I want to first explain to you by looking at 4 different types of laws that are deterministic and time reversible. So let's start with Newton's laws. They are time reversal invariant and deterministic, but within classical mechanics, stochasticity comes in through chaos and irreversibility comes in through friction. Let's first discuss briefly friction. So any classical mechanical system in reality has some dissipation and friction. So it's not really fully time reversal invariant. And some people try to derive friction from a microscopic time reversible deterministic picture, as Wayne has explained just a couple of minutes ago. But later on, I will discuss why these derivations are not satisfactory in my view. And chaos, of course, brings this very sensitive dependence on the initial conditions. And but chaos, viewing chaos as deterministic means to think that there's an infinite precision to the initial state. This means infinite number of bits to describe the initial state. But I think quantum physics has taught us that there is not an infinite amount of information in a finite size system. So as soon as you question this infinite precision, you get indeterminism from chaos, because the initial state, given a finite precision, does not fix the future time evolution beyond some horizon. So let's look at electrodynamics. Next is also deterministic and time reversal invariant. So if you reverse time and reverse the sign of the magnetic field, then you get the same physics. But when you look at the emission of radiation, you bring in irreversibility because you always use the retarded solutions and not the advanced solutions. And the reasoning is, well, now what you do when you do this is you assume that all sources of electric and magnetic field are spatially localized and in the temporal past. So the fields go away, they distribute in space, and eventually they get absorbed somewhere and their energy is turned into thermal energy in walls or in gas clouds. So in some way you invoke the second law of thermodynamics eventually when you justify using the retarded solutions. Quantum mechanics has the Schrödinger, this non-relativistic quantum mechanics is based on the Schrödinger equation, which is time reversal invariant when you take the complex conjugate of the wave function, and which is deterministic, but that's just half of quantum physics. Of course, you have state preparation and measurement. Both are irreversible stochastic events. There are people who derive measurement from unitary time evolution of system plus environment. I'm not a fan of those derivations for two reasons. One is you always bring in the derivation assumptions that are foreign to the theory, namely typicalness, uncorrelatedness, a bit like Wayne mentioned about the classical mechanics assumptions. And the second reason is I'm not satisfied with that it doesn't really explain why in a one-time run of experiment you only get one outcome, which is stochastic. So my view of physics is I want a description of the world that explains this. Quantum field theories have similar problems. They have these two building blocks. One is the unitary time evolution according to the propagator. The other one is preparation and measurement or generation and destruction of the particle, which is again something that's irreversible and stochastic. So I want to defend the view that stochasticity and irreversibility are fundamental ingredients of nature, and that the associated fields of physics, statistical mechanics, thermodynamics are equally fundamental as the other ones. They cannot be derived from the other ones. And I'll discuss this in a moment. And there are famous scientists who defend this view that thermodynamics, especially the second law, is very fundamental, and probably most of you know this quotation by Arthur Eddington. For time reasons, I only read the first sentence. The law that entropy always increases holds, I think, the supreme position among the laws of nature. So as soon as you admit that stochasticity is a fundamental feature of nature, then you automatically get irreversibility. So let's just look at the master equation that describes a very general stochastic system where you have transitions, stochastic transitions between states with rates Wji is the rate of transition from I to j. So the master equation tells you the probability of being in state I increases due to transitions from other states j to I, and it decreases due to transitions out of state I to other states j. And under fairly general conditions, for instance, if to each transition there is also the reverse transition, under very general conditions, you get a unique long-term solution, and you converge towards the unique stationary state given by this equation here, where we just put the time derivative of p equal to 0. So here you have irreversible convergence towards the unique stationary state, which is also a hallmark of the second law of thermodynamics in a closed system. So what about those derivations that derive the second law starting from a deterministic reversible theory? I want to look at classical mechanics. You could make a similar reasoning for quantum mechanics. The issues are very similar in both cases. So in classical mechanics, the argument goes like this. So how you get the second law from deterministic microscopic picture. So you describe the state of a gas, let's say, by a point in phase space. Phase space is spanned by all coordinates and momenta of all particles. And the time evolution then is just the trajectory in this phase space. if you don't want to look at one system, but an ensemble of systems in very, very similar initial states, you start with a finite phase space volume and evolve all these systems in the ensemble at the same time. Then this phase space volume stretches and folds due to chaos, but its size remains the same due to Hamiltonian motion. So if you put a grid over the system, then after sufficiently long time, a bit of this initial droplet will be found in every cell of that grid. That's how the argument goes. So you arrive at quasi-ergodicity. If you look at one trajectory, after sufficiently long time, it visits every cell in the energy shell. If you look at an ensemble, this initial phase space volume distributes just over all cells of the energy shell. And the last step in the derivation of the second law is now you say, okay, you can be anywhere on the energy shell with same non-zero probability, but almost all cells in this grid belong to a maximum entropy macro state. So let's say the macro state is, for the example of the gas, just an even distribution of density in space. And because after a long time, you can be in any of these cells, and most of them, or almost all of them, correspond to the maximum entropy macro state. Therefore, you have the second law of thermodynamics and the increase of entropy. So let's have a closer look at this derivation, because there are some things to criticize or to comment on. First one, I mentioned it already before, this idea of a trajectory, or this idea of a phase space volume that evolves according that an ensemble where each system evolves deterministically is based on the assumption that you have infinite precision of the state. As soon as you don't have infinite precision, the picture changes completely. And I like this quotation from Nicolas Gisin, pretty well-known quantum physicist. Real numbers are not really real. Mathematical real numbers are physical random numbers. So because you cannot write down the initial state with infinite precision, but only with finite precision, you need stochasticity as the time evolution goes on to generate all those digits that you didn't yet have in the initial state. My second comment concerns the quasi-ergodicity. It requires this concept of coarse graining. But coarse graining means that you admit some ignorance. But why should nature accommodate to our ignorance of the precise microstate? If there was something in nature that went beyond what we know about it, then it might behave differently. So there's nothing in classical mechanics that forbids that all the atoms of the gas in my room here are in that corner up there in 5 minutes. Because among all the initial states compatible with the precision that I have, there is also a set of initial states that lead to this unusual behavior. So, and the fact that coarse graining works and gives us the right results means nature herself is coarse grained and has no intrinsic knowledge or hidden variables that go beyond that, what we can do. So, and for the last point, when you argue that, okay, you can be in any of the phase of the energy shell phase space cells after some time, essentially you make an argument of probability, because you assume that all the initial conditions that are compatible with what you know are equally probable. So you make a probability argument. You don't get rid of probability, you just push it back to the initial state. So like hidden variables, the initial state encodes somehow already everything that we will later observe probabilistically to happen. But you prepare the initial, or assume the initial state is a complete random number. In quantum mechanics, you make similar arguments with the infinite precision of the wave function. A huge amount of entanglement, I think you would need a huge amount of precision to describe all that entanglement. And all these derivations, all these quantum mechanical derivations of statistical physics also make additional assumptions of uncorrelatedness, of randomness, and some of typicality also. It's all the same type of thing. So what I like about these points that you can find on this transparency, so phase space points need to be finite, and there needs to be true stochasticity if you want to get the second law of thermodynamics. Both features are satisfied by quantum mechanics because the uncertainty relation tells us that phase-based points have a finite volume. You cannot fix momentum and position at the same time. So for me, quantum mechanics essentially justifies the derivation we do in classical mechanics. So that's just a Wikipedia illustration of the uncertainty principle. And as soon as you have finite precision, as I mentioned, you have stochasticity, because initial state doesn't get encode all the future time evolution. And stochasticity, of course, is an inherent feature of quantum mechanics. It pops up in many different contexts. So for me and for some other people, these events, quantum events where the indefinite future becomes the definite past, are closely related to the passage of time. Unitary time evolution is just a rotation in Hilbert space, which is not really a change. So I consider those events to be true, stochastic, irreversible events related to the progress of time, to the passage of time. Other people emphasize this also. I want to, for the past couple of minutes, I want to put the focus on something that is less often discussed, namely that this stochasticity is related to top-down effects. We often like to think bottom-up, from the parts to the whole. Interaction of the parts gives the behavior of the whole. Of course, there are bottom-up effects, but there are also top-down effects from the wider environment on the system. They are pervasive, and I think they are often overlooked in discussions of scientific fundamental questions. And for the measurement, it's obvious it's a top-down effect because we put up a classical measurement apparatus, so it's a classical environment that brings about the quantum measurement, the transition to a definite final state. And if the Stern-Gerlach apparatus was oriented in a different direction, we would measure a different component of the magnetic moment of the atoms. We would get different results, maybe different probabilities. So really, the context determines the possible events and influences their probabilities. And that's not just true for measurements, but for any types of quantum events. So when there happens a fusion process in the sun, there is this thermal high-pressure environment that is responsible for those transitions, and that it influences the probabilities and the rates of fusion events. So it's everywhere. And it's not just the immediate context, it's a large-scale context, essentially on the cosmological level, the very far from equilibrium situation. Because at each quantum event, entropy of the universe increases. So photons are emitted to the universe, and of course the Earth is surrounded, fortunately, by a cold universe, so it can get rid of excess energy. And I want to point out one more thing. So together with George Ellis, so one of our papers is on wave function collapse and the influence of the environment. And what we do there is we go through all the steps that happen in a real world measurement, from the incoming quantum particle until the pointer gives you a measurement result. And you know, when you look at the best theoretical descriptions of all of these steps, I mean, there's this magnification of the signal, there are avalanches. Only the very, very first step is unitary time evolution. Everything else is mixed theories with elements from classical and statistical physics. So again, that's one of my many reasons not to think that there are few fundamental microscopic theories that include everything else. I want to comment a bit more on chance and top-down or contextual influences. There's a quotation by Karl Popper, which is not related directly here to quantum mechanics. He argues very generally that stochastic transitions have something to do with environmental conditions. So here he says, propensities are not properties inherent in a die, but in something a little more abstract, even though physically real. There are relational properties of the experimental arrangement of the conditions we intend to keep constant during repetition. So it's the context, again, that sets the scenery or the environment for what can happen. And I want to give some more examples just to raise your awareness of influence of the context on probabilistic events. So when an excited atom emits a photon, that's because the environment can take up that photon. If you put the atom in a small cavity, it does not get de-excited. And of course, when you have transitions triggered by final temperature, then you have these stochastic transitions, Boltzmann probabilities, then it's the finite temperature environment that influences all these events. The firing of neurons in my brain is stochastic, but when and where firings happen more often is influenced by even by something so non-physical as my thoughts, logical thinking, my ideas and creative moments. Gene expression is influenced by the environment, so transcription factors bind and unbind to the promoter region in the cell, and these rates are affected by environmental influences, phosphorylative transcription factors, and so on. And biological mutations are also stochastic events that are very context dependent. So let me make some provocative final statements. So I think there are now at least not a small number of fundamental laws of physics that determine everything. I even think physics is not causally closed at all. I don't think the laws at the microscopic level are more important than some others, so I defend a non-reductionist view. And we see determinism and reversibility only in very special, idealized, isolated situations where we carefully protect a system from all influences from the outside. And I think we should look not just at the top-down effect, not just at the bottom-up effects from the microscopic world to the larger world, but also to top-down effects from the larger world to the microscopic world. And I think that's important for making progress in understanding time. Thank you very much.
Thanks for having me. I will share my presentation. Thanks for listening. So being trained both as a philosopher and a physicist, I was very excited about the invitation and this topic, like time and philosophy in physics. So this allows for a lot of combinations and things to do. So I thought what might be most interesting in the sense that it's kind of complementary to the other talks would be to give you a kind of a crash course on time and philosophy, and from there on to move to physics, to see why time is such a pertinent topic in philosophy, and from there to see why topics we discussed already, like relation to causation, passage of time, and so on, are really also of a broader philosophical interest. Okay, so I will talk about why and how and what we are ordering when we consider time, typically in philosophy. Start with a bit of a stage setting, as I said, why time is such an old and pervasive issue in philosophy, then how we order events in time. I will motivate and introduce a standard distinction from philosophy, and we will then see that what of that distinction is actually relevant in physics and what is not. But I think that's important to at least once discuss this distinction. We will come to that, and then we will see what are then topics that are also of interest, I think, for both for philosophy and physics, and then also for philosophy of physics more specifically. But as I said, I wanted to start really very generally with the staged setting, and I thought it would be nice to remind us really of the oldest phrase, the oldest fragment we have in Western philosophy, and it goes back to a thinker, actually and also Carlo Rovelli had worked on, namely to Anaximander, and there we have a phrase kataten to chronotaxin, so according to the ordinance of time. And I think it's nice to remind us as physicists of the fact that this is really the oldest fragment. It talks about time and it talks about the lawfulness of nature. So the context is the following. Anaximander thinks about what the world consists of. So out of those things from which beings are generated, into these again does their perishing take place. And now there's the quote, or what we take to be a quote. According to what is needful and right, for they pay the penalty and make atonement to one another for their wrongdoing, according to the ordinance of time. So here, law is a very broad notion, right? It encompasses, in modern terms, scientific laws, but also natural laws, legal laws, right? It's not distinguished in that context, and it relates it to temporal adjustment. So it's really an old topic in philosophy. And let me also give you a quick idea why time is such a pervasive issue in philosophy. And I will do that by just going quickly through some subdisciplines, philosophical subdisciplines, and you will see that each and everywhere you will find considerations about time, right? If you think about ethics, you wonder about the responsibility for past deeds, for future generations. If you move to political philosophy, you think about the role of the relative timing of elections, the endurance of legislation periods. If you think about philosophy of daily life, Lebensphilosophie, I mean, how to live well, and that often or usually means how to live well over time, or how to live well given our finitude and other related issues. Philosophy of mind, why does time sometimes seem to flow faster, sometimes slower? Or more fundamentally, how does the sequence of perception turn into the perception of a sequence, really? And then, of course, we have the question philosophy of physics, and also the border to metaphysics. How does the direction of time come about? How can time be measured? Is time a continuum or is it discrete? So a lot of the questions that came up already, right? Okay, and to end this stage setting, what's the role actually then of philosophy, or what's one main aim? And I would say that, well, it's about coordinating the human, our experience, right? The things we are doing, the cultural enterprises, different contexts, and then do something like a structural analysis and comparison, rather than being a reductionist from the outset. And this means, and I think this also relates to some of the things that were already said, right? So that we have to distinguish things carefully, not to mix up too many things in the beginning, but to acknowledge that there are different types of time and time scale, right? We might talk about physical time, about time experience. Historians will talk about historical times. And then, of course, the time scale or the units are different ones, right? And it's just important to keep that in mind at the beginning, because if we start to mix up things too early, then we don't get a clear grip on what's going on. And then you will actually realize that a lot of issues about time are really issues about, distinguishing these different events and ordering these events, right? And that, of course, can take place in both within a time scale or within a certain type of time, or across, right? And that leads me now to second part, to the how. So how do we order things in time? What are the typical orders philosophers talk about when they want to order events in time? And I want to motivate it quickly by following a story, kind of a short story by Lewis Carroll. And I'm sorry for those who know this story already, but let's do a little thought experiment, right? I offer you two clocks, and you are asked, okay, so which one would you like to, which clock would you like? So the first clock I offer is a clock that shows the correct time twice a day. And the other option is a clock that shows the correct, the first one is the one that shows the correct time once every 2 years. And the other clock shows the correct time twice a day. And usually if I do it in a course with students, they go for clock B, because they say, well, obviously it shows the correct time more often, right? Okay. So that's the first choice, but then the story continues. So there's another choice of two clocks, right? So we have clock C. It's a bit slow. It takes 1 minute too little every day. So it loses a minute every day. Okay. And clock D is the clock that has stopped. That doesn't work at all. And now if you do it with students, they often then say, well, I choose clock C because at least it somehow works. That's better than a clock, than a watch that's completely out of order. But as some of you might have already guessed, the point then, if you said that, then you did something inconsistent, right? Why is that? Well, the punchline of the story is that, of course, clocks B and D are the same. A clock that has stopped shows the correct time twice a day. If you look to the right, 8 minutes past 10, it shows the correct time twice a day. Whereas a clock that loses a minute every day loses half an hour a month. So it's 6 hours a year. So it's 2 years. It loses 12 hours, and only then it will show the right time. Okay, but now the point is, and so the story continues, that now the guy in the story complains, right? He says, well, but the problem about clock B is I don't know when it shows the right time, and that's why it's crap, right? But now there's a repost that says, well, you do know when it's correct. It's correct at 8 minutes past 10, right? That's the correct answer. And now you see there's something else that is missing at that point. That's the whole thing I want to get across. In order for a clock to work in a daily context the way we want it, you must have the information that when it is now 8 minutes past 10. You need really kind of an index for the present, otherwise it doesn't work. And this motivates a distinction in philosophy that on the one hand, we have what's often called then a B, we have A times and B times. So the jargon here is not very innovative. So a B series is a tenseless order of events. So I might order events just in terms of whether they are earlier or later or simultaneous with one another. So there's no specific points of reference. It's like, for example, like the opening hours of a shop here, right? We have hours, we start counting at our hours at midnight. We could have done this differently, but this is kind of tenseless, right? This can stick to your shop window the whole week, right? Whereas this now open can't stick if it is meant to make a correct announcement for the whole week. So we have what's called an A series, a tensed order of events. You order events according to the fact whether they are present or more or less past or future. And then you have a specific point of reference, namely the present. Okay, so, and now, of course, philosophers then tend to notoriously fight over the metaphysical priority. And I mean, this is not meant to capture current physics. It's just to show the idea that either if you're an A theorist, if you believe that tensed order is fundamental, you believe that maybe only the present exists, or the past and the present, and that it's kind of moving, you have a moving present, or you prefer the view that actually there is no important distinction between past, present, and future. It's only about events being earlier or later. Then you would be a B theorist, or sometimes also called an eternalist. And of course, you might now already see that whether you prefer one or the other, this will have repercussions on the questions I mentioned in the beginning, right? Whether we have responsibility for future generations and so on and so forth. But let's now move towards physics more, because now we see that actually we will see that the B theorists are more kind of closer to the physics. But let me start with the A theorists. People who defend an A theory, who believe that the distinction of temporal events in terms of being present, past, or future, are often philosophers who tend to focus on mental events or subjectivity or experience. Right? Not necessarily so, but it's kind of, as I said, a kind of a standard alliance. And why is that? Well, I mean, if you're interested in mental states, so I put it here in kind of a nutshell, well, I mean, it's relevant whether the dentist is drilling now or not, whether it hurts now. It's not important whether the drilling is at 8 minutes past 11 or 17 minutes past 2, and then I have to double check with my clock whether it's 17 minutes past 2. That's not the way it works, right? But with regard to physics, this point of view is often yeah, well, it's accused or has, of course, problems if we compare it to relativity theory, because if simultaneity is not absolute, then you get into trouble because you then don't have an absolute present, and that kind of crushes your picture there. Okay, so in contrast, B theorists, people who say, well, the important order is in terms of being earlier or later, that is in philosophy often people who are interested more in, let's say, in nature or in physical states, right? And that's because here it's relevant whether some event, or whether a certain time T1 is earlier or later than T2, right? And it's not in any emphatic or genuine sense about the question whether T1 was yesterday, is now, or will be tomorrow. And just to get that clear, I mean, just by calling in a kind of a more general, more loose sense, something present, or call something memory or something, or call something a storage, information storage, I mean, that isn't enough, right? And even light cones, for example, I mean, we write past, present, and future, but it's not about past, present, and future in any genuine sense. It can be translated, and that's kind of the standard test things have to pass. Can I translate it in the end into earlier later relations, right? And as long as that's possible, and if by memory I just mean that something happened earlier and then some information about it is available at a later point, then of course it can be translated. It's not kind of irreducible in any strong sense of past, present, and future. But of course the weak point of that view is that often it doesn't do that well with mental states, right? If you want to describe mental states, where sometimes we have this more genuine sense of things being past. And with that, I come to my last slide. So, okay. So why is that interesting? So if you now think about physics, there are now big philosophical issues, questions that, yeah, but we can see how these general topics fit and relate to issues in physics. And as I said in the beginning, I mean, issues about time are often issues about the ordering of events. Then, of course, you might ask the question, well, but of course, then it would be cool or interesting to learn more about the relation between A and B time. And I just said, usually if you do physics, you're more interested in B time. But of course, since I worked in that area for some time, I should, of course, mention that, I mean, if you do psychophysics or biophysics, you might indeed be interested in that relation because you work on time and perception. And you get kind of a physical approach towards what's happening in perception and thereby maybe into A time. Then, of course, we have questions about the inner dynamics, time and causation. We talked about that. And then a general point, which I think is of interest and still a topic I'm about to do something with a dear colleague of mine in quantum information theory, Renato Renner at ETH. I mean, one interesting thing which I think is still needed is a clearer understanding of the notion of an event. I mean, this holds, of course, within philosophy, if we talk about other areas of philosophy, right? Politics, perception, and so on and so forth. It's not so clear whether people mean the same thing if they say events. But of course, we might also think about that in the context of physics. I mean, if you think about general relativity and quantum mechanics, I mean, on the one hand, an event might be clearly an interval in or of space-time. But if in quantum mechanics, I say, well, it's, let's say, a realization of an observed value, then of course it's not clear from the outset whether this is really the same notion of an event. And I think that this is also an interesting topic to investigate. And I think with that, my 15 minutes are over, and thank you very much.
Yes, thank you very much. Very nice talk and on time. Thank you very much. Is there any questions? Okay, please, Professor Rovelli.
If there's somebody else, I don't want to monopolize the questions. I am happy to give up my. If nobody has a question, I have a question. This was a nice presentation of a discussion that has been going on for long, and you presented the various. But you didn't say how you see it, because so I'm curious about that. I mean, I know about this. I'm a physicist. I'm not a philosopher, but I'm curious about philosophy. So I read and reread 20 times my McCarthy paper that started the A series and B series. I've read about that. I've even written papers myself about that. At the end of the day, I just want your reaction after 10 years of thinking about that. I don't understand what the problem is. I mean, you can define the definition of the A series and B series is perfectly clear. I mean, the distinction between two is it's very clear. But then, so the definition is clear. But then there's the problem is which one is it's what? It's more fundamental. Which one is the right metaphor for thinking about? Then what is the problem? I mean, we use one in certain cases, we use the other in certain cases. We know when one with the other. We know how to deal with time. We have different ways of using the notion of times. Which one is sharply the question? Not something generic like, is time the A series or the B series? The way you've presented it, but that's not your presentation. I mean, the way it's common is that somehow one argues with some metaphors, waving hands, that there is the B theories that think this, the A theories that, and people to some extent do separate themselves in camps. But what is exactly the thesis of one and the thesis of the other, and where is contradicted? Without using words which I don't understand, like fundamental or important. Important for whom? I mean, something is important for me. Do you see what the question? My question. What is sharply the question?
Okay, yeah. Maybe I start the way you put it first. So you ask about my position, right? And
yeah, and that's actually
I think I showed kind of the way out, and I showed what the interesting point is, right? The interesting point is, as you said, there are different contexts, and sometimes we use the A series, then we use the B series. And I think the important point is to get clearer about that. And I think getting clear about the notion of an event is really an important point in that context. And I think that is the thing we should get clear about. And I completely agree. The idea about that's also why I said they notoriously fight over that, right? So I agree that debate has kind of reached a stalemate position, right? And I guess I'm allowed to say that because I wrote my master thesis on that. So I was with Hugh Mellor, so I was really in this debate. And I for like 5 years or 10 years, I had the feeling we can really kind of settle that issue. And then you just realize, well, but in the other camp, there are also smart people. And as long as you have enough smart people in each camp, you have all these kind of, minute details. And then the other one can say, well, but look here. And so I'm also not interested in the fundamentality question, but I'm interested in the question, okay, so there are these two ways of ordering events, and why is and what is an event? Is it a different notion in those cases, and how do we relate these things to one another and get clearer on that? But it's not a question about whether there is a right or a more fundamental notion. That's not what I'm interested in, really.
Thank you very much for giving me the opportunity to present my work here. And my talk is based on a joint work with Marco Di Mauro and Salvatore Esposito. Essentially, I deal with some Feynman's contribution to the debate on the foundations of quantum mechanics, which are scattered in various places, which go from the report on Chapel Hill Conference on the role of gravitation in physics in 1957 to end with the famous Caltech lectures on gravitation, which Feynman gave in the year 1962 and 63. So essentially, these contributions essentially dealt with the main issue in the quantization gravity, main issues regarding putting together quantum mechanics and gravity. So I mean the famous measurement problem in quantum mechanics and the issue of the wave function collapse following a measure, and also the issue of gravity-induced wave function collapse. Okay, and this is the main thread of my presentation. And so I start with a quick introduction in order to show you the places in which we can find Feynman's contribution. Then I focus on two Gedanken experiments which Feynman devised during the discussions sessions in Chapel Hill Conference. And then I show some hints to the solution to the problem of wave function collapse towards a possible role of gravity in it, and I show also some contributions of Feynman to the debate, wide and deep debate on the role of the observer in a closed universe. This is another key feature, and it is deeply linked with the issue of Everett's manifold interpretation of quantum mechanics. mechanics, and then I draw my conclusion. And so the top question at the Chapel Hill conference with on the role of gravitation in physics, which took place in North Carolina in 1957, was is summarized in a question: should gravity be quantized? And this is also summarized in a quotation by Peter Bergman contained the report on the conference written by Cécile de Witt-Moret and David Reichels. And Bergman says that a study should be made of the extent to which arguments based on the uncertainty principle force one to the conclusion that the gravitational field must be subject to quantum laws. So here we see that the problem is that how to put the uncertainty principle and the need to quantize the gravitational field. Okay, and this translates essentially two main points. Can quantize the elementary particles serve as a source for a classical field? And second question, if the metric is unquantized, would this not in principle allow a precise determination on both the position and the velocities of the Schwarzschild disparities of these particles? So again, the problem is the gravitational field must be quantized or not, really? And also, what are the limitations imposed by the quantum theory on the measurements of time distances and curvature? Okay, and what are the quantum limitations imposed on the measurement of the gravitational mass of a material body? In particular, can the principle of equivalence be extended to elementary particles? And really, at Chapel Hill, the problem is that it is possible to make a quantum superposition of two different places of the center of mass of a massive body. Okay, this is the issue. Okay, and Feynman contributions are scattered here and there in Chapel Hill conference, and so in the report by Cécile de Witt-Moret. And there is also some considerations about this issue in a letter which Feynman wrote to Wiki Weisskopf on January in 1961. Okay, in that really the letter deals with the issue of gravitational waves and on the energy content of the gravitational waves, and on how to set up an experiment in order to establish if gravitational waves are quantized or so on. But there is a crucial passage. Okay, maybe they are not. Maybe gravity is a way that quantum mechanics fails at large distances. Okay, and Feynman shows an open mind towards the problem of quantization in gravity. Okay, a very open mind, as this sentence testifies. And a lot of hints towards this problem are scattered in the Caltech lectures on gravitation, which he gave in 1962 and 63. In particular, the section in the lecture 1, the title is very meaningful in that respect on the philosophical problems in quantizing macroscopic objects. And here Feynman says that the extreme weakness of quantum gravitational effects now poses some philosophical problems. Maybe nature is trying to tell us something new here. Maybe we should not try to recognize gravity. It is possible, perhaps, that we should not insist on the uniformity of nature that make everything quantized. It is possible that gravity is not quantized and all the rest of the world is. So he wondered if it is possible this, and he wondered if it is possible that there is an asymmetry of nature, so all is quantized, but gravity, it is not quantized. But okay, these are the places where Feynman's are scattered. Now we focus on some of his contributions by starting with the quantization of the gravitational field, which is the topic of discussion in section 8 at the Chapel conference, and the focus was on the contradictions arising eventually in the logical structure of quantum theory if we don't assume gravity quantization. And so really the validity of class theory of gravitation relies on the smallness of the experimental fluctuations at the scale where gravitational effects become sizable. So Feynman came into play with his one of his famous Gedanken experiments. Here we see in particular a gravitational two-slit experiment in which we have a mass indicator, a mass detector behind each slit. And so we work in a space-time region where the linear dimension is L, the time dimension is L over C. And then here we can, we can write the uncertainty on the gravitational potential in general in this way, in terms of LP, which is a Planck length. Then the order of magnitude of the potential generated by a mass M within the spatial part of the region under study is this. Okay, and then if the time of observation is less than L over C, by comparing these two delta G, we can infer the following mass uncertainty, that is about 10 to minus 5 grams, and indeed, if we allow an infinite time, instead one would obtain M with infinite accuracy on the other side. Okay, and Feynman concluded that the last option could not take place, okay, for a mass M which is fed in these apparatus, and so eventually this apparatus will not be able to uncover this difficulty, okay, unless the mass is about 10 to minus 5 grams. So the conclusion is that either gravity must be quantized because a logical difficulty would arise if one did the experiment with a mass of order 10 to minus 4 grams, or else quantum mechanics fails with a mass as big as 10 to minus 5 grams. Okay, but this is the first experiment. Okay, but this is only a first contribution, because the discussion goes on at Chapel Hill. The discussion goes on the quantization of the gravitational fields, on the also on the epistemic, also on the wave function at an epistemic concept by Belinfante, and so on. Okay, and Feynman introduces a second Gedanken experiment, which is a very which is a crucial one in order to pose the problem of the existence of the role of gravity in producing the wave function collapse. And this second experiment is a kind of a Stern-Gerlach experiment with the gravitational apparatus. Okay, and here clearly emerge Feynman ideas and the meaning on the quantization. So we have okay, a Stern-Gerlach apparatus, so we have a beam of spin 1/2 object, and so this beam enter a Stern-Gerlach apparatus with the two counter 1 and counter 2. One counter, each one counter is connected by means of a rod to a massive, to a ball, okay, to a ball with a diameter of about 1 centimeter. So the ball has the possibility to go up or down depending on whether the spin 1/2 object goes into counter 1 or counter 2. And so in principle, if we carry out a quantum mechanical analysis, okay, we can derive, we can give an amplitude, okay, for the ball up and the ball down, okay, and also because the ball has a macroscopic size, it is able to produce a gravitational field which may be used to move another ball, for instance, a probe. Okay, and so here we see that the gravitational fields is a channel. Okay, is a channel between the object and the observer, and Feynman says that there must be an amplitude for gravitational field, provides that the amplification necessary to reach a mass which can produce a gravitational field big enough to serve as a link in the chain does not destroy the possibility of keeping quantum mechanics all the way. There is a bar possibility, which I shouldn't mention, that quantum mechanics fails and becomes classical again when the amplification gets far enough, because of some minimum amplification which you can get across such a chain. But aside from that possibility, if you believe in quantum mechanics up to any level, then you have to believe in gravitational quantization in order to describe this experiment. And really there is a question by some guys at the discussion, Chapelil in particular, Bondi, and Feynman remarks that there is an amplitude that it is up and an amplitude that it is down, a complex amplitude. This is the ball, okay? And as long as it is still possible to put those amplitudes together for the interference, you have to keep quantum mechanics in the picture. So why it is important, the discussion of this Gedanken experiment by Feynman, because it is this Gedanken experiment is the basis for the discussion of the problem of wave function collapse, and here Feynman needs to some kind of decoherence as a possible solution, okay? And here it is clear that in Stern-Gerlach, in this Stern-Gerlach gravitational experiment, the source of decoherence is the amplifying mechanism, okay? And when there is a huge amount of amplification, okay, then amplitudes switch to probabilities, and then we have a wave function collapse. And there is okay, this is a conclusion of Feynman, okay, about decoherence, okay, and any piece of equipment able to amplify by such and such a factor 10 to minus 5 grams and so on necessarily must be of such a nature that is irreversible. So it is decoherence. Okay, it might be true, but at least it would be fundamental because it would be a new principle. There are two possibilities. Either these principles, this missing principle is right, or you can amplify to any level and still maintain interference, in which case it's absolutely imperative that the gravitational field be quantized, I believe. Or there is another possibility which I haven't thought of. So here, there is Feynman means to the role of decoherence, but now the problem is what is the source of decoherence? There are a lot of possible sources of decoherence, and here the Feynman means to a decoherence of gravitational origin. That is a possible gravity, role of gravity in produce decoherence, okay. It assumes that quantum interference might eventually take place with a mass of macroscopic size, okay. And this triggered a lot of a huge amount of research, for instance, by Roger Penrose, which is a famous Newton-Schrödinger equations and so on.
Excuse me, I apologize. The time is over.
Okay, I conclude.
Thank you very much. Thank you.
I conclude, okay. thank you very much to you. Okay, and so okay, I conclude by saying that these observations and these hints by Feynman, led to a lot of research on spontaneous collapse theories and so on, also on some a lot of collapse mechanisms. See, for instance, also Liosh-Diosi theories, also models by Girardi, Rimini, Weber, and so on. Okay, so this is a main issue. The idea is attractive because gravity is ubiquitous in all interactions, and so gravitational effects depend on the size of objects. Okay, and okay, thank you very much. Okay, time is finished, so I skip the last issue, that is the role of observer. Thank you.
Thank you very much for this opportunity to talk here. It is so my background from earlier times is a constructive axiomatics of space-time, and so I'm here asking for the realization of time, that is for the physical time. So this is the outline of the talk. Yeah, this is a philosophical remark here. You all know that Kant made something. It's a nice wording in German. Muss insgesamt im Gemüte bereit liegen. That's very nicely phrased here, and that we have now different time standards here, and this is, so to say, the graph historical account on how time changed. So the compatibility of these two theories then led Einstein to formulate special relativity. So we come from absolute time to relative time. Then the compatibility with the special relativity and Newton gravity gave general relativity, leading to a dynamical time. And quantum mechanics rests on an external time. And the question is, what is there? But I will not go to quantum gravity also. I will just keep in classical and quantum theory. So I'm asking for the time in various theories or branches of physics. So in electromagnetics, I will not go into weak or strong interactions, but compare this with gravity. But again, gravity is different. There are at least two types of clocks, maybe three, so we will discuss that. And one issue I want to address here, and this was mainly the main motivation for me, but now it comes out a bit different, but nevertheless, so it was how we can describe changes or fundamental constants, whether one has to rely on the other theories, or can one detect changes in the charge without gravity and vice versa, changes in the gravitational constant without electromagnetism, and so but this is not so, yeah, you will see. Time and general relativity. So if you are in general relativity, Einstein equations, geodesic equation with the affine parameter ds, and this S is then the proper time, and I will explain now what the proper time is. So if you have now an observer and a distant event, then we can send the light ray back and forth, and light is unique in general relativity. There are only one light ray in one direction, in one future direction, and by this you can, if you have a parameter here, you can relate this distance to a certain parameter. We are now assuming that there's any parameter, some kind of parameter, and we just identify this. Yeah? And then we can determine by this light ray the distance, and if you have, so to say, if you have the situation that we have an observer and a particle passing by, the observer need not to be in a geodesic motion, then the observer every moment sends a light ray to the particle, it will be reflected, and so you have a kind of distance measurement here, the relative distance. In this parameter, with respect to this chosen parameter on the world line of the observer, we can now differentiate that, and then we get the relative velocity can be described in this way because we already have g from the behavior of light in space-time. And from that, you also can describe the relative acceleration. This is a bit more complicated formula, not too complicated, but too much to be shown here. But then we can now make a requirement, and this has been formulated by Volker Perlich. An observer equipped with a standard clock measures for all freely falling particles the same x double dot over 1 minus x dot squared. That is, all the freely falling particles show the same relative acceleration given in this term. And this is also reasonable that if one particle is freely falling, then the other should also be freely falling in terms of the relative acceleration measurement. And this exists, such a parameter exists, and this parameter is called proper time. So this is an operational definition of time in general relativity. You do not need anything else. It is so general relativity tells you what good time is. Then we have to check whether the atomic clocks are standard clocks in this sense. Okay, this can be shown. So there's a paper of Parker and Pimentel 40 years ago. They calculated the energy levels of a hydrogen atom in curved spacetime and found that the energy levels will change with the curvature tensor times the Bohr radius squared. And this would lead to a relative change of the frequency of the order 10 to minus 42. So for practical purposes on Earth, this is far beyond any experimental relevance. Of course, near to astrophysical black holes, this may play a role. Yeah? Then atoms are no longer standard clocks in the sense of general relativity. And these standard clocks are the clocks by which we define the gravitational redshift, the gravitational time delay, the gravitomagnetic clock effect, or all the special relativistic effects, the time dilation, Doppler effect, and so on. So this is the time we are always talking about, and this is to very high accuracy realized by atomic clocks. Now there's another clock in general relativity or in gravity, which is defined by the motion of test particles around gravitating objects. So we know this from Kepler's third law. So the angular velocity squared is gm over r to the cube. This can be rewritten in this way. Or if we compare two particles, 1 and 2, then we have that the square of the orbiting time over the radius of the cube of the radius of the particle is constant. Is constant for all the objects, and by this you, for example, can see that the Pluto needs 10 times as long as a Mercury, or no, this is the velocity. So you can compare this with all the observations in the solar system, and this fits very well. This is, you cannot measure, or by this here, this is invariance against variations of G and M. So here, if you have already a scale, you of course can measure G times M, but if you are just measuring the time, then these relations are invariant against G and M. This changes, and the parameter R is just given as a this is a parameter, and from this time comparison we can derive what is the ratio of the two orbits, and from that we can get the function of R2 or the R2 as function of R1 if we measure these two times. From that we can determine the radius or of the circular orbit of the second particle, just in the units of the radius of the first particle, and this is what we want to have here. So this is a unitless equation. We can use this, we can make the same thing in general relativity for Schwarzschild. There, the Kepler third law looks exactly the same, so we get the same equation here. But this is the coordinate time. So if we transform this to the proper time, and of course we are moving together with the Earth, with the atom clock on the Earth around the Sun, we are measuring the proper time. Then we get this relation here. And then if we now compare the times of two objects, yeah, of Earth and Mercury, then we have a modification here. That is, we are able to see changes in G and M of the product G and M. So the coordinate time is invariant in this sense, but the proper time sees the mass of or G times the mass of the central object. You can also make this for other space-times, Reisner-Nordström. So you see here the coordinate time, the proper time looks a bit more complicated. And then if you again take the ratio of the times, then it depends on q squared over m for the proper time, for the coordinate time. So it is insensitive with respect to the gravitational constant. But here, if you have the comparison of the proper times, we see a dependence also on the gravitational constant. So we can, so this is really sensitive to q squared over m, to g. We can factorize g, and this yeah. So it is sensitive to all these parameters. Yeah? And one also may make this more complicated by using charge particles. Then you have an additional coupling, and then one can get further results. So that means we have here clocks by which we can explore the structure of space-time, yeah, while in a or the structure of the gravitating object. Yeah, so and of course also the function of R here, which is behind these relations. It would be also good to discuss, and this is something which has not yet been done, at least to my knowledge, to study such kind of bound system in an external gravitational field. So let's take the moon as a test object, the Earth as gravitating object for the moon, and then to take both in the gravitational field of the Sun. And then it would be interesting to check whether this time given by the Earth-Moon system, whether this also shows the gravitational redshift or something like that. So this is something what has to be done. Okay. Another, so this means that here we have two times of clocks. First is a proper time, which is just given by the geometry, and the gravitational clock, which is given by the underlying space-time. Okay, and the relation between these two is then here, yeah, shows dependencies on the parameters underlying the space-time. Also, another issue which is not really related to that, but has to do with time. So you know this Taub-Nut space-time, which is violating everything what we think about gravity. And few years ago, we calculated all the orbits, and mainly Hagman did that. The geodesic equation of this space-time is inseparable, so you can really completely integrate this in terms of elliptic function. And typically, the orbits are lying on a cone, but this is not the point here. So here are a few orbits. But what has the point here is that the Taub-Nut space-time possesses no curvature singularity. So it's a perfect regular space-time, but it is geodesically incomplete. In the sense, it is of course not a regular space-time. And the point is that during the second transition through a horizon, the proper time terminates. So if you have a particle going on here, this is the first crossing the inner horizon, again the inner horizon, and then the proper time terminates, while another function goes to infinity. But the proper, so gamma is, so to say, the amino time, which is related, the amino-Sakharov time, which is related to the proper time. So here the time terminates. And here we have seen that we have here this is a type of orbit which shows this property, and you see in the Z R plane, a kind of déjà-vu figure, the particle goes through the horizon of the inner, through the inner horizon, and then goes back. It goes to negative radial coordinates and then comes back, and so this is here where so to say the time ends. This is for point particles. It would be interesting to discuss this for fields. As I would remind, and probably you know this discussion of Horowitz and Demarov, who discussed the issue of singularities in the presence of fields, not of point particles, but in the presence of fields. And Letellier and other then calculated many examples. So there are spacetimes which have a classical singularity, which the quantum fields do not see as a singularity. So this should maybe interesting to calculate here. And even more interesting, I find that this is what happens to real atoms. There's no singularity, but the real atom has some extension, and what may happen here. So first one takes the wave function of the center of mass, and then another wave function of the internal structure, and then look what will happen there. So, but this also is something what maybe would be interesting to deal with. Time in quantum mechanics is, there is nothing new. All these energetic effects like the electronic transitions, the fine structure, hyperfine structure, the vibrations, rotation of molecules, cavity frequencies depend on the fine structure constants, also ratio of electron and proton mass. And but since the energy levels depend on various powers of the fine structure constant, any time dependence or the dependence can be extracted from the measurement. So there's nothing really interesting to see here, contrary to my expectation. So you can really measure all these things exactly. And if you want to compare that, there are some all possible dependencies on constants. At least if you take general relativity with all these orbits and quantum mechanics, which is on the previous slide, all the constants can be measured within the respective theory. There's no need to relate to the other theory. The question is whether is there some extra by comparing Maxwell and Einstein? I do not see that. Sometimes there are some theories with a varying E, with a time-dependent charge, which leads to a time-dependent fine structure constant, which have some kind of a relation to geometry, but I do not see that it is really necessary to have that. This is this relation. This is what I just meant. It is not clear whether there is really a necessity to refer to the other theory. So everything can be measured. And another question is whether these constants, the C, the H bar, and the Boltzmann constant, might be time dependent. I think these constants are not coupling constants. G and E are coupling constants, while these constants are not coupling constants. They are more, so to say, you can relate the temperature to an energy. So these are conversion factors, nothing else. Yeah. To me, it seems that these are just conversion factors. To making C time dependent makes absolutely no sense from the the causal structure of space-time. And here I do not see that these are physical units. They are just conversion factors from temperature to energy and from frequency to energy. And I also do not know whether there are consistency relation between the time dependence on all these constants. Okay, so this is what a kind of brainstorming with respect to the topic time and the practical realization of the time. So I showed that there's a standard clock defined by the, or it relies on the equivalence principle. Of course, this is not in the empty space, so that there are some principles behind that. There are clocks based on the gravitational dynamics, and one can all determine these parameters within the GR and also within electromagnetism. What should discuss more general space-times, one should also discuss the two-body problem. There's another time scale, the chirp time, and perhaps this adds another time scale there. And then we should have 3 time scales, but this has to be analyzed, so the result is there. And then, of course, one should check whether these gravitational time scales show the same gravitational redshift, and one should discuss the time dependence of all constants. So thank you very much.
All right. I want to thank everybody, the organizers and Shakufa, for letting me speak before this prestigious group today and be a part of this event. I'm talking about explaining the passage of time, and hopefully it will let me switch my slide. There we go. I want to dedicate my talk to the memory of 2 departed friends, Ray Monroe and Greg Kirk, who both emphasized the need to develop a top-down approach of math for physics to complement the normal way we do things. A major motivation was a conversation with Tevi and Dre at GR21, where he affirmed that it's unavoidable that we need to use non-commutative and non-associative geometry in various physics settings. Back in 2000, Alain Comte sparked my interest in intrinsic or modular time evolution. Recent work by Tahinder Singh, the theory of ions, has increased that interest. And Carl Rovelli's book, Reality is Not What It Seems, and his article in the Foundation Physics showed me how profoundly necessary it is to incorporate philosophy into our study of physics. So we have these age-old questions. How do we perceive time? How do we measure time? Why does time even exist? Why does it only move forward? Why do our choices accumulate? But now, why does the gravitational wave signal arrive earlier than the photons? So we wonder, is time the same for everyone or everywhere? So we have all these different viewpoints. The ancient and modern philosophers, neither could really agree on much of anything. We have common everyday experience of time, the scientific knowledge and theories which disagree in some measure with our common experience, but we have a common and standardized clock time, which makes people have a false impression that we live in Newton's common river of time, or that's a proper way to view the universal or cosmological time. But relativity shows us a different picture where 2 different observers can have a very different picture, and not only perception, but measurements of time will differ for moving and stationary observers. But it asserts we can look at time as a block from the outside. The 4D block time is a very common way to look at things. But quantum mechanical time, on the other hand, assumes that time moves forward as a constant. So we wonder, is there an intrinsic time? The metaphor of the stepping in a stream from Anaximander is very rich and meaningful an analogy for the flow of time. That if we assume that it's comprised of atoms, the molecules of water moving downstream get replaced by new atoms. So in actuality, it's a quantum mechanical as well as a classical analogy. That the classical, measurable attributes may remain largely the same on the macroscopic basis, but microscopically we know they're different. Painters and bakers, when they are working their craft, need to pay very close attention to the order and sequence of all the things they're trying to do. If you try to bake the cake after you mix the ingredients, that works. But if you try to bake the cake first and then mix the ingredients or frost it before you baked it, it doesn't quite have the same effect. So but this also emerges in the study of non-commutative and non-associative geometry, where you really have to pay careful attention to the execution of steps and to follow a rule of direction and sequence. But this occurs in everyday situations. Our observations and decisions will ratchet the action forward. And whatever we do, we're going to have to live with it because our experiences accumulate. But it's a determination every step of the way. Every measurement we make is a construction that we're choosing a particular point of measurement and a particular target. The determination is a process with two phases because we're observing and creating or projecting at the same time. Determination also takes time because we have to bracket things if even for real numbers, as Nicholas Giesen said, they may be constant in a way, but to determine the actual value, well, how many digits do you want? It takes time. And the choice of what to observe and which elements also accumulate. But if we're in an airplane, if we're pilots in flight, that the order in which we take our maneuvers is just as important as how far we execute each turn, because the order it's a non-commuting rather than a commutative system. But what does this give us? Non-commutative measure spaces evolve with time, according to Kohn. Where does this happen? Well, higher dimensional spaces, quantum mechanical spaces, but if we had infinite degrees of freedom, what would this imply? And what does this mean as far as the evolution of time? The Tomita and Takasaki theory of modular Hilbert algebras revealed that there are evolutive properties when we take separate out the linear and antilinear parts and then use that to create an operator for a complementary algebra. We find that things automatically move forward. This actually occurs in Chinese philosophy because the doctrine of Wuji agrees in many ways with the view of Kohn. The unformed essence, beyond and before distinctions or polarity, is neither light nor dark, neither large nor small, and that's something about the non-commutative nature of things. The variations come first and then conditions arise later. So Wuji is the evolution that occurs before the appearance of form in the non-material or matter-free regime. Accordingly, the Chinese word for physics is Wu Li, because physical reality is described or seen as a process. The maths of non-commutative time evolution come about because we're talking about how the infinite maps to the finite. I saw a wonderful lecture by John Clowder, where he was explaining how this is the essence of quantum field theory. But we find that as degrees of freedom approach infinity, the evolutive properties Kohn was talking about become more or less automatic. He offers the following relation, and the outer automorphisms arise as a quotient between the full automorphism group and the internal or inner automorphisms. I like to refer to an old joke in German that was ist los, was nicht eingebunden ist, what's up, what's happening, whatever's not tied down. So modular time evolves through equilibrium states, Kubo-Martin-Schwinger EQ, equilibrium, and so it's a thermodynamic process of things winding down for any positive temperature, because the conjugative space combine iteratively or add on top of each other. We're used to living in a place where we take a lot for granted. That we see things as being relatively constant, but it is easier or maybe better to assume that variations give rise to constant condition. The ordinary maths we use satisfy the conditions of everyday life, but for theoretical physics and discovering the origin of time, we may have to look a little bit further beyond the edges. So how do we get here? We look at the norm division algebras. Briefly, very briefly, the Newtonians 8 dimensions, and that 7 of them are imaginary. So the imaginary components greatly exceed the real components. And the imaginaries can be viewed as degrees of freedom, freedom to vary by a specified amount in a certain direction, orthogonal to the reals. Well, we fix 4 of 7, we fix 4 of the 7 axes, and then we get the quaternions. We fix 2 of the remaining axes, we get the complex numbers, where there is an equal number of degrees of freedom and of degrees of fixity. And they're very well behaved. So the complex numbers and the reals get a lot of use, whereas the quaternions and octonions get more or less ignored. But we're used to living in this space where we're examining the maths as from the viewpoint of an island of solid or condensed matter, where all of the familiar rules apply, but the general numbers, the more general cases, that isn't always the case. So we have various theories of higher dimensional origins, and these are more or less chronological order. But that gives us some rationale that a higher dimensional origin could exist. What does this get us? It resolves the hierarchy problem, or the weakness of gravity, moves the Planck scale to an earlier epoch, provides a spontaneous mechanism for inflation and the origin of time, creates an arena for a 4-dimensional universe on the boundary, because the surface of a 5D sphere is 4-dimensional. But if bubbles occur in the early universe, they can grow to the size of our present universe. So I'm imagining the present day cosmos is likely a 4D bubble. Plato had something to say that time is the image of eternity, and this relates more to what we know as duration or the persistence of objects. But spaces also must persist in time, or we wouldn't have an arena for things to exist in. So space-time as a fabric is kind of an essential for the existence of subatomic particles, and we need to have a certain amount of volumetric space, or the quark-gluon plasma would be all that existed in the early universe. But we know that things did evolve to create spaces in which the particles can appear. So we look next to the question of the wave function. Is it real? Is it just probabilistic? Is it energy? Is it theory? Well, in some ways, the wave function may be more fundamental than the particles. H.D. Dieter believed strongly. He wrote an article, there are no quantum jumps, nor are there particles. And we had some interesting correspondence. His viewpoint is rather radical, though, that the quantum wave function exists, but particles don't. That's very unusual. And most people can't wrap their heads around that. But the appearance of a collapse depends on our having a stable framework, a condensed matter platform to measure things from. And otherwise, we wouldn't observe them collapsing. Well, our friend Peter Morgan has devised a theory using Koopman-von Neumann theory, and suggests that we can either look at a collapse or a non-collapse, depending on whether we're seeing it from ordinary space or non-commutative space, and thereby fine-tune the parameters, whether we want to see it from one viewpoint or the other. So hopefully we can reconcile the time arrows, because the quantum mechanical and thermodynamic time arrow don't always seem to agree. But if we see space-time is by nature non-commutative because space and time are connected, we have something emerging where a possible different way of looking at things from the outside can help to clarify things. The point of overall patterns, I'm speaking to the idea of the end of the universe, or the asymmetry, the gross asymmetry of time that some of the earlier speakers addressed, that time is globally asymmetric, and I think it might be because math is asymmetric.
Excuse me, may I have a short comment in between?
Are we near the end?
Yes, the time is almost over, but we are waiting for the organizer to close the session. It's out of my hand. I just want to say a few words about thank you everybody to be here, and it's a very pleasure to have you all here in this talk. But we can,
couple of slides.
Yes, we can still listen to your talk, but my apology if it's just happened to be closed very quickly. Continue, please.
So the gist is that math is not a blank slate, but there are patterns behind the mathematics, and we have to discover some of what the missing pieces are by going beyond the common and look to the fringes of and restore the heart of math and philosophy to physics. Thank you so much, and I appreciate your time and willingness to watch my talk. Thanks again.